We're continuing with Chapter 2 in the trigonometry textbook. In this video, we're going to go through section 2.4, which is on solutions and applications of right triangles. So now that we can find trig function values of any angle using our calculator, and we understand why we use the calculator to do this, and also we've learned how we can solve for angles. If we don't know an angle, but we've got some side length information, we can solve for angles using our calculator with inverse trig functions. But we haven't officially talked about inverse trig functions yet in full detail. We're going to do that in another chapter. But still, we can solve for unknown angles with our calculator. We know how to do that. What we're going to talk about in this section and even the final section is the idea of solving right triangles. And it sounds like we're going into some fancy new application that is going to take a little while to learn, but the idea is really simple. All they're saying here is that the idea of solving a right triangle is you have a situation where you've got a right triangle in any orientation. Just you have a right triangle you're dealing with for some reason. It's in any orientation in 3D space, and you have some information about that right triangle. You know either one angle, or you don't know any of the angles, or you don't know an angle. You know some sides. Like, you have a portion of the information, but you want to solve for the rest of the information about that right triangle. So you want to know each of the side lengths and each of the angles. And then with that, you've solved the right triangle. But what we're going to do, though, is we're going to work a bunch of application example problems in the upcoming videos that involve solving right triangles. And these are really interesting, and they're really helpful to build your intuition of applied trigonometry. There's examples of things that like surveyors use. They're trying to find the length across a lake, and so they can easily measure a distance, mainly measure this distance, and then based on they use a line of sight to get some angle, and then they can, with trigonometry, they can solve for like the distance across the lake. It's things like that are really interesting. You might have a spot that actually, it's very difficult to measure the exact length you're looking for, but you can use trigonometry and lengths that you can measure to solve for those unknown lengths. So we're going to work a bunch of examples like this, which are, again, it's really going to help to build your intuition of applied trigonometry. Now, in the previous section, for the example problems, we worked a bunch of kind of applied trigonometry example problems. So what's the difference? Well, the only difference is with these examples, we're dealing with like actual geometrical triangles. That's the difference, right? So like this surveyor example, this is an actual triangle. In section 2.3, those were like, it's always right triangles no matter what. It's always trig functions are always about a right triangle in some sense. But like we had, the velocity of a car was going in this direction, and then the radar detector was measuring the car with respect to like the speed with respect to this direction. So you have these two separate speeds, and let me draw this a little longer. You have these two separate speeds here. So those speeds form like a right triangle, and so that's where the trig functions come in. But it's technically not an actual like geometrical right triangle, right? You see, that's what we're talking about in these last two sections, but it's still kind of one and the same thing, honestly. It's all trig functions. If you have a trig function, that trig function is based on the definition of trig functions. It's rooted in right triangles. You can't have a trig function without a right triangle. So, okay. The beginnings of trigonometry can be traced back to antiquity. Figure 19 shows the Babylonian tablet, Plimpton 322, which provides a table of secant values. Wow. The Greek mathematician Hipparchus and Claudius Ptolemy developed a table of chords, which gives values of sines and angles between 0 and 90 degrees in increments of 15 minutes. Until the advent of scientific calculators in the late 20th century, tables were used to find function values that that we now obtain with the stroke of a key. Applications of spherical trigonometry accompanied the study of astronomy for these ancient civilizations. Until the mid-20th century, spherical trigonometry was studied in undergraduate courses. That's interesting. So, spherical trigonometry was like typical for undergraduate courses until the mid-20th century. An introduction to applications of the plane trigonometry studied in this text involves applying the ratios to sides of objects that take the shape of right triangles. I'm not sure what they mean by spherical trigonometry, but with plane trigonometry, we're always, everything we've learned so far and everything we're going to talk about in this entire course, we're always in a plane, either the plane of the computer screen or like a plane in any orientation in 3D space, because we're always dealing with a triangle or like a circle, like where we're in a plane. And it's really powerful that we have our calculators that can give us trig function values of any angle. It's really powerful. And so since we have our calculators, and since we understand the definition of trig functions, and we understand what our calculator is doing when we input, the sine of an angle or whatnot, then if there's any situation in real life that it involves a right triangle, or it closely takes the shape of a right triangle, the application, then we can use trigonometry to solve that problem. And it's going to involve doing what? It's solving the right triangle. Like, based on the information we have, we can use trig functions to find the side lengths. Okay, so they go into significant digits here. We're not going to get into significant digits. I've got a full video on significant digits in the physics playlist if you want to check that out. Significant digits for angles. We're not going to get into this here. So yeah, solving triangles. To solve a triangle means to find the measures of all the angles and sides of the triangle. That's the idea. That's solving a triangle. And as shown in figure 22, we use lowercase a to represent the length of the side opposite angle A, lowercase b for the length opposite angle B, etc. So that's common convention. We talked about this in geometry, but you have angle A, B, and C, and then the side opposite those is the same letter but lowercase, opposite those angles. That's a common convention. So solving a triangle means you solve for all the angles and the side lengths. And now that we have the power with the power of our calculator, the fact that we can easily get accurate numerical or exact values for trig functions if it's a special angle, then, or we could also solve for an angle with known side lengths. We have the tools we need to solve triangles. Well, right triangles we're talking about here. So solving a right triangle given an angle and a side. So what would we do here? How would we solve this right triangle? We're given an angle and it's in minutes, which it's like a decimal, to decimal precision of an angle. And we have this side length. Well, this is easy. Okay, we just pick a trig function that involves the hypotenuse. So the sine of this angle is lowercase a divided by the hypotenuse. Solve for lowercase a. The cosine of this angle is lowercase b divided by the hypotenuse. Or we could have done secant or cosecant. Solve for b, and then you're done. Well, this angle we could have solved for in the beginning. You just do 180 minus 90 minus this. But you just need to, the key is you have to put into your calculator the level of precision. Now, they're going to talk about significant digits, and you don't want to report a higher precision than, that's not, I'm not going to get into that here. We're just going to solve the right triangle, and we're not getting into significant digits in this course. And you might wonder, well, why not? The reason is because to me it becomes overwhelming. We're going to be working these application example problems, and it's hard enough. We're trying to learn the trigonometry. Then you add on, we have to follow the significant digits, and then you add on that we're trying to think about, word problems are difficult. You're trying to think about how the application, it's overwhelming. We're just going to report, I'm going to round to whatever. We'll make sure that what's given, we'll input this as a decimal into the calculator, but we're not going to be tracking significant digits. Okay, so they solve for lowercase a, lowercase b, and angle b, and that's it. Solving a right triangle given two sides. Okay, well, to get the third side, you could use the Pythagorean theorem, right? Or you could go another route if you wanted to, but then you just say like the sine of b sine of a is opposite over hypotenuse, so then you just need to use the inverse trig function feature on the calculator. So this is all really easy. We'll work examples, but this should make perfect sense to you how you could solve a right triangle. Okay, angles of elevation or depression. In applications of right triangles, the angle of elevation from point X to Y is the acute angle formed by ray XY and a horizontal XY within point X. The angle of depression from point X to point Y is the acute angle formed by any XY and a horizontal ray within point X. So the difference is that the point Y is, if it's an angle of elevation, it's above X. If it's an angle of depression, it's below X. So angles of elevation or angles of depression are just, you're measuring an angle with respect to the horizontal, and it's always it's an acute angle. So that makes sense, right? If you think about an angle of elevation is going to be an acute angle that's measured like above the horizontal. So it's what is the angle of something above the horizontal? That's an angle of elevation, an acute angle though. If it's below the horizontal, it's an angle of depression, but it's always relative to the horizontal. Be careful when interpreting the angle of depression. Both the angle of elevation and the angle of depression are measured between the line of sight and a horizontal line. Yeah, it's always relative to the horizontal when you think about angle of elevation or depression, relative to the horizontal. Okay, just the problem-solving techniques here are outlined. Okay, finding a length of given the angle of elevation. So if you're given an angle of elevation here, it says you can measure that you're 123 feet from the base of the flagpole, and somehow you know the angle of elevation from that distance from the flagpole to the top of the flag, then you can solve for the height of the flag, right, using trigonometry. Angle of depression here, you know how high you are up a cliff, and you know how far that cliff is from a light tower. So then you could find the angle of depression from you to the base of the light tower. Now, if I was going through school right now studying trigonometry for the first time, my question would be, well, how are you going to measure? This is pretty cool. Like here, this is really cool because, yeah, I could measure my distance from the flagpole. Okay, great. But then how are you going to get this angle of elevation? And my answer to that is I'm not 100% sure. Feel free to comment if you have an answer to this, but I think that's like kind of the things that surveyors do. Those machines can like find angles of elevation like this. And so they measure off with those rolled tape measures, and those machines are good at finding angles, so then they could get heights and whatnot. Heights of mountains and things like that. So we're going to work a bunch of examples like this, and it'll give you a good feel for applied trigonometry. But again, you can see though how these examples, they involve actual triangles, actual geometry, as opposed to that velocity example. That's not an actual geometric triangle we're dealing with, but it's still trigonometry. Like breaking velocities down into components, perpendicular components. That's not geometry, but it's still trigonometry. It involves right triangles, like indirectly. Okay, let's work some example problems.